Welcome everyone. Thank you for coming to this seminar of our NITheCS series. Our speaker today is going to be Jonathan Hakata, who is finishing his PhD. We have seen some initial drafts of the thesis, so that's good news. We will therefore meet deadlines. I won't go into too much of detail about his background, just to point out that he contacted us from Rhodes University. The postgraduate world with a name like Hakata. I thought he was Japanese. When he pitched that here, he could be Japanese. And so, I mean, rather than talk about sciences, he got many skills. You would have noticed that at our conferences, he's a good singer and a dancer. He plays the bar very hard at the karaoke. I just want to draw a contrast with him and one of my earlier students. That was Jeff Funzio for a long time. He was working, publishing papers, etc. But there was a gap always between the number of papers and the number of children. So I've noticed Jonathan, I think it's 2 papers and 3 children. And is that over to you.
Thank you very much, Prof. Thank you, everyone. And, first of all, I'd like to thank the organizers of this seminar series. Actually, they go a long way in trying to mold us as upcoming researchers. So I'm so grateful to have given this opportunity to share what I've been studying for the past 3 years. So today I'm going to talk about the 1+1+2 formalism in the study of spherically symmetric spacetimes and its applications in studying gravitational energy dynamics. And of course, I've managed to accomplish this work under the supervision of these 2 great men. I'd like to thank them also for being patient with me. They molded me from a weak background to what I am today. It's very unfortunate I can't see Prof G, but maybe he's busy on something very, very important. Okay, so this will be the framework of my talk. I will give a brief introduction, some theoretical rationale, and this will be a building block to what we published in this third section, shear-free spherical fluids. And then I will then talk about the 1+1+2 formalism in studying the gravitational induction and causal temperature profiles. And lastly, I'll give a summary of our findings. All right, let me point out that 3 and 4 are based upon some written articles. Some have been published and some are still under review. Okay, so coming to the introduction, in 1915, Albert Einstein, through his famous theory of general relativity, postulated that, in fact, what we perceive as gravity is actually, what we perceive as a force is actually the interplay of the gravitational interaction caused by the curvature of space-time. And he put forward the well-known set of equations known as the Einstein equations, which basically comprise of a set of partial differential equations. These describe the fundamental interaction as a result of space-time being bounded by mass and energy, and they can be written like that. Now, RAB here is the Ricci tensor, which encodes the curvature of the space-time. And of course, R is the trace of the, we call it the Ricci scalar, and it is the trace of the Ricci tensor RAB. One can view the Ricci scalar as the magnitude of curvature at a point. GAB is the metric tensor, which describes the geometry of the space-time. G is the gravitational constant, and TAB is the energy momentum tensor of matter. Now, due to the highly nonlinearity of these equations, the closed form solutions of these equations are hard to come by. There have been ongoing research ever since the theory was propounded. Researchers are trying to find solutions of these equations. Of course, several techniques have been employed to further simplify these equations and get some solutions. And of course, today, like the title of my talk emphasizes, I'm going to have a look at one of those techniques to further simplify these equations and try to get some solutions. Now, coming to the theoretical rationale, in general relativity, of course, as I mentioned, we use different formalism, different techniques to solve the Einstein field equations, depending on the physical situation in the problem. For example, I remember very well when I was doing my master's at Rhodes, where we were trying to investigate the propagation of gravitational waves. So in that setup, in which we have a numerical code that can produce some simulations, we found out that the Newman-Penrose formalism worked very well. So various formalisms, they work perfect in different setups. So we have plenty of them actually in literature. So they are used to reformulate the Einstein field equations and try to solve. We have the well-known 1+3 covariant formalism that was, okay, that originated from the early works of George Damois in the early 1920s and was further refined by Ellis, also studied by Ellis and recently republished by Ellis in 2009. So this technique, what it does, it formulates the Einstein field equations into first order differential equations, which are much more easier to work with by splitting spacetime into three spatial hypersurfaces, of course, that are parameterized by time. By this, we mean to say that each hypersurface, three hypersurface, is parameterized or is indexed by time. And maybe someone might want to understand the term spacetime. By spacetime, we mean that it's a four-dimensional continuum that combines time and the three usual coordinates of space that we know. All right, so the end result of this technique, of this space decomposition technique, will be a set of dynamic and kinematic quantities which will carry all the information of the system, and the field equations that we come up with from these dynamic and kinematic quantities can then further be analyzed to extract some physical meaning. Now, a further decomposition of the 1+3 technique will give rise to what we call the 1+1+2 covariant formalism. So this was put forward by Clarkson and Barrett in 2003. So in this space-time decomposition technique, we kind of isolate a preferred spatial direction of rotation, and we call that direction EA. So this will give rise to the time-like unit vector. Of course, UA is the time-like unit vector, and of course it is normalized, and the preferred spatial direction that we isolate is EA, also gone out to UA, of course, and the two remaining dimensions are they remain untouched. So hence the name, the one stands for UA, and the other one stands for EA, and the two are the untouched dimensions, right? Now, for instance, the metric tensor, for example, in the 1+3 formalism, which is the mother of 1+1+2, it can be written like that. And the further decomposition of this equation 2 in the 1+1+2 formalism, then it can be written like that. Where HAB and NAB here are the projection tensors. This in the 1+3 projects all the vectors. HAB takes all the vectors that are orthogonal to UA onto the three hypersurface, and NAB here projects all the vectors that are orthogonal to UA and this preferred spatial direction EA onto the two sheets. Okay? This decomposition is well suited for locally rotationally symmetric spacetime. Of course, since I mentioned somewhere here that we isolate a preferred spatial direction of rotation, so locally rotationally symmetric spacetimes are those spacetimes which have a unique characteristic that there is a preferred spatial direction of rotation at each point. So therefore, to study such spacetimes, we implement this spacetime decomposition technique. Now, let me just point out a few important objects that we need further. So for example, the energy momentum tensor can fully be defined in the 1+1+2 technique like that, where mu is the energy density, and UA is the time-like unit vector, and P is the isotropic pressure. And of course, the Q that is appearing here, I'll define it further down. It's the heat flux, of course, and pi is the anisotropic stress in the space-time. And of course, there are these two important derivatives that we will be using throughout the research. And we have the dot derivative for any tensor psi. It is defined as UE nabla this. This dot derivative is basically it gives the evolution of a quantity along the time-like sense, and the head derivative, we call it the spatial derivative, which gives the change in the spatial along the spatial direction in EA. These are very important derivatives in our findings. And of course, since we are taking these derivatives on a manifold, on a curved manifold, then they don't generally commute, and therefore they give us this important commutation relation. Now, this relation, equation 7 is in general, but it simplifies significantly whenever you assume, say, spherical symmetry. Some of the quantities will be identically zero, and then just a small piece will remain of that commutation relation. So this is very important in our findings because it will give us integrability condition for our scalar A to be calculated later on. For both cases, for spherical symmetry classes and for thermodynamic processes. Now, in general, the 1+1+2 variables, that this is the full set of the variables. Of course, these variables are entirely defined in terms of U and EA. Remember, UA is our time-like unit vector, and EA is the isolated spatial direction of rotation. So all these quantities are defined in terms of UA and EA, and therefore, okay, for example, theta, which is the volume expansion scalar, is defined as dA where d is the derivative, is a derivative operator, is a spatial derivative operator. And of course, we can define the rate of acceleration A as U dot AEA. Okay, so the rest of these variables can be defined in various manners using dA and EA. Now, omega defines the vorticity, sigma is the shear, the Kelly E is the electric, and H is the magnetic part of the viral tensor. Phi is the sheet expansion, two sheet expansion. Remember, we are in 1+1+2. And psi is the rotation. Mu is the energy density, as I mentioned earlier on. P is the isotropic pressure. Phi is the anisotropic stress. And Q is the heat flux. Now, these are the scalars together with their two vectors and projected symmetric tensors. Now, in general, if we then implement all those variables in this space decomposition technique, then we get a huge system of equations. There are about over 30 equations, but here I'm just showing you some of them. That's why I indicated some yeah. These are some of the equations. So I just wanted you to have a feel of how the general equations look like. So these equations, some of them are evolution equations, some of them are propagation equations, and some are mixed equations, and some are divergence equations. example, 9 and 10, these 52, they have dots. This is phi dot and psi dot. These are evolution equations. Of course, they will tell us how, for example, the sheet expansion evolves over time, and the rotation, how it evolves over time. Of course, 11 and 12, if you look at 11 and 12, they are mixed equations. They contain the derivative and dot derivative. 11, I'm sure it's quite famous to most of you, to some of you rather, because it's known as the Rachel-Dury equation. Of course, if you look at maybe 40 and 15, 40 gives the divergence of the vorticity, and 15 the divergence of the electric part of the biotensor. So these are just some of the equations. Then because of time and space, I didn't include the rest of the equations because we are going to assume some further simplifying assumptions, so we don't need the entire system. Now, coming to the shear-free spherical perfect fluid case. Now, let me point out that in locally rotationally symmetric spacetimes, like I mentioned before, these are spacetimes. Okay, if we mention the class 2 specifically, it's a class of spacetimes which are inhomogeneous. What we mean by inhomogeneous is that we can have different parts of our background expanding at different rates, and therefore we end up reducing. And of course, they have the inherent property of high degree of symmetry, high degree of symmetry, and then those two properties, they reduce the general equation significantly, and you end up with this huge mass system here. Now, of course, the only set is containing the only set of variables is now reduced to that, which is a theta, phi, sigma, e, and that. Maybe someone may ask me, why did we drop off all the vectorial and tensorial quantities? Now, in this class of spacetimes, there is no change in the physical properties of the spacetime. So therefore, all the changes, the vectorial quantities, they vanish. That's why you don't see any vectors and tensors in these equations. But we note of the fact that we don't have an equation for A dot and theta yet. And also we don't have an equation of state. So this means that this system here is not closed unless if we impose an equation of state, and if we define also these two missing guys, A dot, which is the evolution of the radial acceleration, and the propagation of the volume expansion. So in shear-free LRS2 perfect fluid equations, we further impose that in shear-free, as the name suggests, this sigma, which stands for shear and the heat flux, when there's no shear, there will be no twisting of the congruence in the time-like congruence, and therefore the heat flux will be zero, and anisotropic stress will also be zero. Keys implemented in the previous system would reduce we further simplify the equations to this system here, and immediately, okay, this was published in that paper last year, and immediately we noticed that we have recovered the propagation equation for theta, and so we remain with one task to obtain an equation or an evolution equation for the radial acceleration A. Now, and it is important to note that at this point we assume an equation of state of this form P equal to P mu, depending entirely on mu. So from these we obtain expression in the next slides. We will obtain expression for A dot, and from that we will then come up with the various classes of shear-free LRS2 perfect solutions defined by or characterized by this acceleration A. Now, in the event that we don't have acceleration, if acceleration is zero, then from the equations themselves, they will point out to the fact that P hat will be 0. So if P hat is 0, then it means that pressure is homogeneous. And therefore, again, just note that if A is 0, there is no acceleration, then equation 29 23 from the previous slide. Together, you the KE, which is the electric part of the power tensor, to be 0, and which then implies that mu F is 0. Now, since both A is 0 and the electric part of the magnetic of the power tensor is 0, then, and also we have seen that P is 0, we find that beta is homogeneous, then this points to the fact that the space-time is necessarily of Friedmann-Lemaître-Robertson-Walker time. Now, on the other side, if the acceleration is not 0, then after some sweat, of course, we were able to get the equation for A dot. So after attaining this A dot, remember this was the missing line. So therefore, it makes the system closed because we now have an equation of state P equal P mu, and we now have the equation for A dot, and of course, theta hat is there. So for compatibility, this A dot that we just calculated, that we derived from careful combination of the equations, for compatibility, this A dot, for it to be compatible with the entire system, it must satisfy the commutation relation that I gave earlier on, which is now simplified because in LRS2 space-time simplifies to that expression. So then our next task is to plug this A dot into this equation and see if it gives us the term on the right. If it does so, then it's compatible with the system. Now, we did that exercise, and to our surprise, we were able to come up with this residue. And of course, for compatibility, for A dot to be compatible with the entire system, this residue must be 0. And of course, grouping like things together, factorizing theta, you end up with this nice expression here. Now, from this expression, we can immediately see for us to attain a 0, either theta is 0 or the square bracket term is 0. If theta is 0, then it points to the fact that the space-time is necessarily static. Or on the other hand, if theta is not 0, then either A, the acceleration, or the electric part of the power tensor, which is the KE, are both 0. Now, if that's the case, if theta is not 0 and both A and E are all 0, then it comes down to the earlier case, Friedmann-Lemaître-Robertson-Walker type. Now, on the other hand, if then A and E are all defined in non-zero, then equating this square bracket term to 0 and simplifying things nicely, we end up with this nice fraction here. This, I would like to call it a new constraint. We obtain this new constraint that needs to be satisfied by the equation of state, by an appropriate equation of state. Now, and even if we evolve this constraint over time, it must be satisfied even in the higher order derivatives. Okay? Until now, so maybe before we go there, let me just emphasize that this is an interesting case. Because in this particular case, we have theta not equal to 0, A not equal to 0, E not equal to 0. This is very, very interesting, and we will continue after this summary. Now, until now, we have extracted these classes of space-time. This kind of a summary of the classes we have identified so far. We have identified that when acceleration is 0 and theta is 0, you can immediately tell from the field equations themselves that it's not physical. You won't get any class of solutions for this choice of parameters. But now, if A is 0 and theta is not 0, we have seen that from the field equations, immediately the electric part of the power tensor becomes 0, which then implies mu H is 0. And that class of space-time is known as the Friedmann-Lemaître-Robertson-Walker type. And on the other hand, if acceleration is not 0, if it's well defined, and if theta is 0, then remember we have shear-free perfect fluid solutions. And these, together with these conditions, they point out to the fact that the space-time is necessarily static. And lastly, this is an interesting class of space-times in which A is not zero and E is not zero. They are both well defined, and x1 theta is not zero. This is giving us, of course, this class is known as the dynamic inhomogeneous shear-free class. This is very interesting, and from it we obtained this constraint that I just mentioned in the previous slide. We will continue to investigate further. Now, as I mentioned earlier on, that constraint, if it's satisfied once, it will always be satisfied even if we evolve the system. So now, differentiate for this constraint to time evolve consistently, this time derivative should always be zero. So if we evolve the previous constraint once, we end up with this second expression in which the g that is appearing now is defined, depends on you, and it's defined in terms of like that. Now for consistency, this second derivative of the constraint and the first constraint that I defined earlier on, they must equate. These two expressions for E over H squared, they must equate. And if you equate them and simplify stuff, you get this nice master differential equation right here. Now, this master differential equation needs to be satisfied by an appropriate equation of state. And of course, as you can see, this differential equation is non-autonomous, but it can be made to be autonomous by making this change of variables. If we do the change of variables, I'm sure you are able to see this. It's a little bit smaller, but I wanted to accommodate everything on one. So now, as you can see, this is now the fourth order differential equation in X, another way of representing that master equation. And we tried to solve this equation using linear laws, but we couldn't find any. We tried also the power laws, we couldn't find any that solves that. And then immediately we said, okay, let's try to visualize the solution numerically. Able to come up with this numerical solution. And this equation restricts our for the equation of state. And therefore the dynamic inhomogeneous is each diameter content. Now, an investigation of the stationary points of this fourth order differential equation pointed to the fact that the fourth derivative is equal to 4 over 9x cubed after doing some manipulation, of course. And clearly, this will only be zero if x approaches infinity, indicating the existence of a singularity at infinity. Okay, so let me take you through to gravitational induction. And ladies and gentlemen, besides the nudity in the picture, there is quite a lot that we can make from this nice art. This was drawn by Michelangelo in 1915, in 1512 rather, in 1512, in the 16th century. And what he depicted here was the creation of man. What we have on the right, I will try to interpret it to fit what I'm going to talk about. So what we have on the right is an idea of God himself. And in the background, we see that there is a brain-like structure, which indicates that God is all-knowing and his muscular is all-powerful, but he infused all of these attributes into man, not all, but some of them. He's rich in everything, but as you can see, the index fingers of these guys are not touching. But as you can see, Adam looks exactly perfectly the same as his creator, but there's no contact. What happened? God infused some of his attributes in man. So, ladies and gentlemen, this introduces the aspect of gravitational induction for me in a nice way. There's a problem that has been existing in GR where we want to understand the transfer of energy from one point to another between two systems via a proper mediating force. So in classical electromagnetism, of course, energy transfer through electromagnetic induction and electromagnetic radiation is well understood. And as well in Newtonian gravity, we understand gravitational induction very, very well. Of course, we all know the moon and earth tidal locks. But in Newtonian gravity, there is no coverage about gravitational radiation, yet it's a well-established phenomenon in GR. Again, GR, we don't have an explanation about gravitational induction, which remains a challenge due to the lack of a suitable energy momentum tensor for free gravity. Now, in classical electromagnetism, of course, okay, we're here. Martens and Bassett in 1998 proved that the Bell-Robinson-Paul tensor, written as TABCD, can act as a super energy momentum tensor for gravitational fields, and it can be defined entirely from the Weyl tensor CABF or CABD. It's the Weyl tensor, and this is the double dual of the Weyl tensor, and it's of the order -4. Now, this tensor, they say it can describe the energy momentum tensor for gravitational field, but its drawback is the order, because the usual energy momentum tensor of matter is of order -2. So that was a major drawback. But of course, Clifton, Ellis, Tapakau in 2018 propounded that if you take the square root of the Bell-Robinson 4-index tensor, you come up with this 2-index square root tensor, and we call it TGAB, and this can stand as the energy momentum tensor for free gravity. Next, normally taking the square root of the tensor is not that easy, as we do with numbers. Of course, it will only be applicable in this special type of spacetimes, in this type D, type N. So in our particular case, we are studying, doing our study in spherical symmetry, so you'll be able to take the square root of the Bell-Robinson tensor for the 4-index. Now, the energy momentum tensor for free gravity, it encodes the energy associated with gravitational waves. It is divergence free. That's a very important quality in vacuum. And of course, it is symmetric about its indices, and it's stressless, just as their counterparts in electromagnetism. Now, gravitational energy transfer is relativistic. It's a relativistic thermodynamic process that is distributive in nature. So we expect the heat flow to have some sense of causality and to be highly stable. So therefore, to explain the aspect of transfer energy from one part of the universe or one system to the other, we need a model that takes into account the aspect of causality. And until now, we have only one theory that can explain that process. And that theory is called the Israel-Stewart, that was put forward in 1979, Israel-Stewart theory. This theory, it has some causality and a high degree of stability, unlike the previous attempts using the ECAT formalism, which lacks causality. From using ECAT formalism, researchers found out that the thermal waves, viscous waves that were involved in the study ended up propagating at infinite speeds, which basically violates the principle of causality, and therefore that was the drawback. But that doesn't mean that ECAT formalism is very, very bad, like what Prof. Goswami said at some point, when Prof. Maharaj mentioned last time. Even if a theory is bad, don't throw it away, because it helps us. It's a stepping stone we modify it slightly and get to fix things until we get the perfect theory. Now, the modification of the Hakata formalism, or Hakata theory of formalism, gives rise to the Israel theory. Now, of course, in assuming a spherically symmetric background and a 1+1+2 covariant splitting, the only set of variables is that, according to Goswami and Ellis in that paper, the only variables that survive, of course, vorticity is not there, right? But sigma is appearing. So this system is different from the previous. And of course, A dot is not here. So to make it complete with the equation of set P equal P mu, you can make it complete by calculating A dot, which we did and published. But I didn't give you the A dot that we calculated because of time. So now we define the gravitational induction energy momentum tensor IAB with these properties that I mentioned earlier on. It has to be conservative. The inductive process, it has to be a conservative process. So therefore, it's divergence free. And secondly, in vacuum, the induction tensor IAB should give us the energy momentum tensor for free gravity. And therefore, it has to be linearly related to some indirection tensor epsilon IAB. Now, of course, these can be derived from these two properties. You can tell explicitly what the energy momentum tensor for free gravity is, and also we can derive the interaction tensor epsilon IAB, and it contains Q in its expression here, which is the inductive heat flux. Now, it is interesting to take note of the fact that Q should obey also these two equations, 47 and 48. This inductive heat flux should obey those two. And from the integrability condition, we, of course, remember the coefficient that I get down. In terms of Q, it can be written like that. And that Q, one that I showed you in the previous slide, must satisfy this condition 49. Now, if we obtain the Q dot head and the Q head dot from the previous slides and plug them into this equation, you can uniquely identify Q to be this expression 15. Now, this is the inductive heat flux. And therefore, from the Israel thermodynamics, as explained in Martin's 1996, the heat transport equation in general can be given by 51. So as you can see, it has some vectorial quantities. So if we project it along EA and expand it, of course, and simplify further, we end up with expression 52. Tau here is the it takes into account the causality effect, and T is the temperature of the fluid, of course, and lambda is just a constant together with T to tau to incorporate causality. Now, if we then replace in this equation 52 with their inductive counterparts, like if we replace Q with the inductive Q and T with the T2 that is the inductive temperature, we end up with the equation, this equation 53. Now, this is the first order PDE for inductive temperature to the T, whose solution always is subject to some more defined by that condition. Now, let me just try to summarize everything that we've discussed so far. We have obtained a classification of all shear-free spherical symmetric spacetimes characterized by the acceleration A and the expansion theta. And we have again answered this question: what causes the shear-free spherical effect fluid to be inhomogeneous with tidal effects? And now the answer to that question is the fact that a suitable equation of state that satisfies the mass differential equation will cause that. And we constructed an energy momentum tensor for gravitational induction IAB. From this divergence-free property, we got the new set of conservation laws, which are the Bianchi identities. Divergence-free is matching also the divergence-free of the energy momentum tensor T theta. Using IAB, we have demonstrated the existence of a temperature function in the final equation that I've just shown you. Of course, using the causal is assured thermodynamics. Apart from spherical symmetry, for future work, maybe we may try to apply the same kind of reasoning to general spacetimes. Of course, general spacetimes under the petrol D or petrol type N, from which we can obtain the square root of the Bell-Robinson tensor for index. Let me stop here. Thank you very much.
Thank you very much, Jonathan. Comments, questions? Somebody?
I want to understand the physical process of this gravitational induction. What is actually happening?
Okay. So basically, in a nutshell, we have induction in basic terms is the process of transfer of energy from a higher energy source to a lesser energy source. So when we say gravitational induction, of course, gravitational radiation, we understand. But gravitational induction, we seek to understand that how does energy in the universe be transferred from one point to the other? With which tensor can we describe that process? Until now, there is no induction published, accepted induction tensor, IAB, that is, there is nothing so far. So this is an attempt to find an induction tensor to explain the process of energy transfer. In a vacuum, that tensor should be, okay, of course, it should be conservative and it should be divergence free. It should exhibit those two properties, yet it explains the process of transferring energy from one point to the other.
I think the connection made the papers that he's described, his feeling is that it must be some way related to tidal forces that are tensor. But still not clearly completely. Any other questions, comments? I just wanted to, a lovely picture, it's fine, but you have a and Mr. Goswami was trying to make a link with that direction. There have been other attempts where people try to look at famous paintings, relating it to physics. And the most famous connection was made with the Nobel Prize winner, Chandrasekhar, where he was able to relate the equations of general relativity to paintings of Monet. And in particular, he also wrote a book on this. He wrote a book on this. In particular, one of the paintings, he was able to find the connection with the first dimension. That's just an aside. So if there are no further questions, let's thank our speaker again.